Quick overview of section 2.4, calculation of the average rate of change. We're going to kick it off with a very simple example using this table, which we could also recognize as a function. It also could be something that we could graph very easily. We're just going to work with the table on this go around to answer a series of questions. And this function that we see here is represented by water level in a very large container. It's just telling us how deep the water level is at different hours of the day. So at its hour 0, the tank started off at 22 feet of depth. At 1 hour in, we were at 33, so on and so forth. And so a series of questions come out. By how many feet has the level changed from the first hour to the fourth hour? Well, the first hour we were at 33 feet. When I got to the fourth hour, 67 feet. What was the change? 67 minus 33 or 34 feet. I'll keep moving my hand bit by bit. From the fourth hour to the eighth hour, well, hour 4, we were at 67 feet. Hour 8, we were at 43 feet. What's the rate of change this go around? 43, our value at time of 8, minus what? Our value at time of 4, which is 67. And we'll come up with an answer of negative 24. So the water level went down by 24 feet. So what we're seeing here is what's called the net change. How much has the level changed from one observation to another? And then we can also do what's the average rate of change? Well, the average rate of change is nothing more than what we call our net rate of change divided by the length of time in which we were measuring. So literally it's what? Change in feet over number of hours. And we could call that change of hours if we wanted to. This little symbol here, this triangle, means delta, change in feet over change in hours. Okay, so what's the average rate of change between the first and the fourth hours? Well, we know that we went up 34 feet. How many hours did we span? 3 hours. The average rate of change is nothing more than 34 over 3. In our second example, we went down by 24 feet. So what was the average change of the water level between the fourth and 8 hours? Well, negative 24 for the total amount that we changed, the net change in that period, divided by how many hours? In this case, 4. We were going down by 6 feet per hour. And there's your average rate of change. So net rate of change, all you're doing is, if you really think about this is an x coordinate, this is a y coordinate. All you're really doing is measuring the change in y over the period of interest divided by the length of that change in y over the change in x, which sounds hopefully very much like a slope. So we'll pick this up in a couple seconds, just flipping into the main pieces of the video. But again, carry this little table with you. It's a nice little simple representation. Again, this is something you could graph on the XY scale and come up with all these answers as well. So now let's go into the heart of the video lesson, section 2.4, the average rate of change of a function. And what you just talked about a second ago using our little water level example is our average rate of change was nothing more than our change in y over our change in x. And we'll do this over, we'll call it an interval that runs from a to b, which you can see graphically here. Notice that our value of b is always greater than a. And we can say, well, can we evaluate this function and get a y coordinate when x equals a? We sure can, and we'll call that point f of a, the y coordinate. When we evaluate the function at b, we're going to get what? A value of f of b. So the change in the y coordinate is nothing more than f of b minus f of a. What's our change on our x coordinate? It's nothing more than the distance from a to b, which is nothing more than b minus a. So we can represent for any function the average rate of change from point a to point b is nothing more than what? Evaluate the function at b, subtract from it the value of the function at a, and divide by that length of b minus a. There's your change in y over your change in x. And if you look at it, it maps out very, very simply to what? Nothing more than the slope of a line. That's what change in y over change in x should sound familiar a bit. And all we do is what? We connect those 2 points with a line. There's your y. You can see it right here, f of b minus f of a. That's your change in y. And what else do you have? This length, b minus a, which is your change in x. That's what the slope of that green line that you see there is. Nothing more, nothing less. Putting it together, if we went back on the other side and we asked that question, what's the average rate of change of the water level between the first and fourth hours? We said the answer was 34 over 3. Well, if we worked from a function standpoint, what would we say? F of 4 is equal to 67. f of 1 is equal to 33. What's the average rate of change from that period, from the first hour to the fourth hour? Well, here's the function, f of 4 minus f of 1 over what? 4 minus 1. F of 4, we already said was 67. F of 1, we said was 33. Divide by what? 4 minus 1, how many hours? 3. 67 minus 33, 34. 4 minus 1, 3. Final answer, 34 over 3. So make sure you're comfortable with this general purpose formula, and obviously the formula that you see up here. All we're doing, evaluate the function, f of a, f of b, subtract f of b minus f of a, that tells you your change in your y coordinate. B minus a tells you the run, how long your x coordinate has been traveling. Change in y over change in x, and you're home free. In the last piece of this video, we're just going to work through 2 examples computing some average rate of change for a couple of functions. Now let's go ahead and pick up and work through a few examples. We're given a function g of x, x squared minus 1. You can see a graph of it, and we're going to find the average rate of change between the following points. From x equals negative 2 to x equals negative 1. You can follow that little dashed line. That slope is what we're looking for, as a matter of fact, for that average rate of change. And then we're also going to look at the average rate of change when x runs from 0 to 2. That'll be represented by the slope of that line. So remember, think about these 2 red dashed lines map up perfectly to this little green line that you happen to be seeing here. Change in y over change in x, slope of that line. So the average rate of change, remember, negative 2 to negative 1. We always make our value of b bigger than a. So remember, we're moving from a negative 2 to a negative 1. That's the direction we're moving. And so to find my average rate of change, make sure that you follow the structure of the formula, f of b minus f of a. So in this case, my b is negative 1, my a is negative 2. And my average rate of change, you can see I've plugged in properly to the formula. There's f of b, g of negative 1, which, by the way, I plug in negative 1 and square it. I'm going to go ahead and get a value of, excuse me, as I plug in a value of negative 1, I'll wind up getting a value of 0. So I know that g of negative 1 is equal to 0. I know that g of negative 2 is equal to 4 minus 1, which is a value of 3. So 0 minus 3, and then what? B minus a, negative 1 minus a minus 2, negative 1 plus 2, that'll be 1. And what's my change? Negative 3 over 1. My average rate of change is negative 3. And if I look at that slope, that's exactly what I see. What did I do? Well, I went down 3 with my y coordinate. I went over 1 with my x coordinate. Change in y over change in x. Negative 3 divided by 1. Second example, the second piece, they want the average rate of change from x equals 0 to x equals 2. Well, this is our value of a is x equals 0. Our value of b is x equals 2. So b fits here. So I'm going to want to have f of 2 minus f of 0 over 2 minus 0. What's f of 2? Square 2, subtract 1, I get a value of 3. What happens here when x is equal to 0? 0 squared minus 1, I'm going to get negative 1. So 3 minus negative 1, and we know that 2 minus 0, that's our change in x, is nothing more than 2. 3 minus minus 1, 4 over 2. My average rate of change there is 2. That should intuitively at least make a little bit of sense. Look, we got an upward slope in this example. It better be positive. We have a negative slope over here. It better be negative. Now, one more piece to do. We're just looking for a general purpose solution here. This is something called the difference quotient. I'm going to look for a plus h and a. Those are my 2 values this time. H is a positive number, so a plus h is always bigger than a. What does f of a plus h minus f of a over a plus h minus a look like? And I'm going to write it out here just so we have a little bit more space. Our function again was, what do I have? I have x squared minus 1. So actually I should use the letter g just to be consistent here, because that was the name of our function, but I think we have the idea. Okay, so how do I handle this first? I need to take a plus h squared minus 1, and from that I'm going to subtract what? A squared minus 1. That's what I would wind up doing up top. over a plus h minus a. That's just going to be good old h. If I expand, I'm going to have a squared plus 2ah plus h squared minus 1 minus a squared minus a minus 1 plus 1. So let me just move my handwriting. Sorry for that as I expanded what's up here. Notice again, I'm subtracting a squared minus 1. That's why I have minus a squared plus 1 over here. This is all over h. What do I notice happens? My a squareds cancel each other out. My minus 1s cancel each other out. And I'm left with nothing more than 2ah plus h squared over h. And what does that give me when all is said and done? It gives me 2a. Let's break it into two fractions just so you can see it. 2ah over h plus h squared over h. And what would I wind up with? 2a plus h. So that's what my difference quotient, what we call here, or the average rate of change for this function from a to a plus h, is going to be nothing more than the example that we just came up with, 2a plus h. So just be comfortable, familiar. The key thing in this exercise is really just being good with working the first couple pieces, the version A, the version B that you see here. But all the other pieces will come into play and be helpful as well. So there's our difference quotient. And then in our last part of this video, just take a quick pause here, review what you've seen, work it out by hand for yourself as well. And then we'll work through this last example where we're going to have a linear function versus the quadratic function that we just did above. Example to work through is just doing average rate of change for a linear function. H of t equals 3t plus 2. Now this is a line with a slope of 3. So I hope that you realize already that for any place, whenever you have a line, well, the average rate of change should always be, no matter what points you're working through, should always be equal to the slope of that line. But let's just prove that. We should get an answer of 3 a couple times here. Let's see what happens. H of t is 3t plus 2. Find the average rate of change. And we're going to use the same intervals before. From -2 to -1. We'll also do from 0 to 2, just like we did in this problem above for a quadratic function. Well, if t equals -2, 3 times -2, -6 plus 2, I get h of -2 equals -4. If I put in a value of -1, I'm going to have 3 times -1 plus 2, -3 plus 2, I'll have a value of -1. So here we go. I'm going to do h of -1 minus h of -2 over -1 minus -2. That'll become a good old 1 down here. H of -1 we said was -4. -4. Excuse me. H of -1, my fault, -1 minus h of -2 minus the -4. -1 plus 4. I'm going to have a 3 over 1 and get an answer of 3. Matches what we think should happen. T equals 0, t equals 2. Well, my A is 0, my B is 2. 2 minus 0, that's going to be 2 on my denominator. I need to calculate f of 2. 3 times 2, 6 plus 2 gives me 8. So I know that 8. And what's h of 0? 3 times 0, 0 plus 2. 2. 8 minus 2, 6. 2 minus 0, 2. 6 over 2, 3. Exact same slope. And then we'll do that difference quotient thing one more time. We're going to do h of a plus h minus h of a over a plus h minus a. Our denominator, by the way, is just going to become a good little h. We'll come back and work that in a few. What's h of a plus h? Well, it's 3 times a plus h plus 2 minus, and we know h of a is nothing more than 3a plus 2. So that's just working the top part. That's my net change. 3a plus 3h plus 2 minus 3a minus a plus 2 minus a 2. What happens here? And this is just, again, I'm just working with my numerator, what we would call our net change. The 3a go away, plus 2 minus 2 goes away, and I'm going to be left with nothing more than 3h. Net change, change in y, change in x, 3h over h is nothing more than 3. And so what we would get, our average rate of change, equals 3. It's constant, again, because this is a line, so that's not necessarily any type of, it shouldn't be a surprise in the least bit. There is, what do we notice, a difference quotient? When we do this for general purpose form for a quadratic, we get 2a, so our value of a matters, as well as our value of h in determining what that average rate of change is going to be. For a linear function, the average rate of change is constant, and it's equal to what? The slope of that line. So there's section 2.4 for you. Hope you feel comfortable with it.